Good morning, everybody, and welcome back to another Resilex webinar. This is the third installment in our series. And for those of you who are new, the Resilex project is a Horizon Europe project that aims to retrieve critical raw materials from waste streams and transform it into valuable materials for specific value chains. And one of these value chains will be the subject of this webinar today. So I'm joined by our esteemed colleague from the Resilex project, Maria Wallin from NTNU, Norwegian Technology University of Norway, and Mickael Albaric from CEA in France. So welcome back, and a few words from my side before going into the details. You can check the Resilex project website to see the results, to grasp the results through our fact sheet series. Then you can discover specific details through the videos. Actually, these two videos that we recently published are exactly focused on the topics that we will treat today. And then you can also retrieve the previous webinars that we did, one about the Critical Raw Materials Act from the European Union, and one about the design of new solar cells and modules using the materials and the research results developed in the Resilex project. So, few housekeeping rules. You can use the Q&A tab to post questions to our speakers. We will proceed in order, first Maria, then Mickael, and then we will take some questions in between the two presentations and at the end. So I really encourage you to post your questions in the Q&A tab so that I can handle it and pass it to our speakers. So enough from my side. I will give the floor to Maria for her presentation. You're muted, Maria.
Now, sorry for that. Thanks for the introduction. Now also, just put it up again. Now you have it in a good mode.
Yes.
So, thanks a lot for inviting me to be part of this webinar. This is the title of my presentation, my part. So we really, as I stated, also work on decreasing the dependence of critical raw materials. And as you can understand from what was shown is silicon that we're working on here. And to then to make the solar supply chain stronger. And we have, of course, focus in Europe. And just the title of the whole EU project, Resilex, is reducing the EU dependence on this critical raw material, then the silicon. And our main aim is to reduce the dependency in EU then on this from third countries, develop a new carbon-free and more efficient process for the production of silicon, and also recycling end-of-use solar PV panels for production and lithium-ion battery cells. And you will see from our presentations that we mainly worked on the silicon recycling side and on the production of PVs from this or on that side, and not on the battery part. And the consortium you can see at the bottom. But who am I? What are we doing at NTNU? We're working on the smelting part, the processing. So we are doing recycling. So you can see the furnace here. This is one furnace that we used during our pilot trial that I will talk about later on. But Norway, why are we interested in this project? We are a country that produces a lot of non-ferrous metals. You can see here on the map, you have Norway there, and all these boxes represent different smelters or metallurgical industries that we have here in Norway. And the yellow ones, that's the silicon plants that we have. So we have 3 producers here. So this is a very important area for Norway. And we are important for Europe, as I will show later on the production of silicon. And my group in general, what we're working on is industrial high temperature metallurgical processes, both on the chemical reaction, mass and energy transfer, and phase transition. As said, we mainly work on non-ferrous metals because that's the industry we're having here in Norway. So not much steel at all. We have 1 steel, but that's it. Recycling is hot for my group and what I'm working on, which you will hear more about here. And also to develop new and processes, and also to improve the current processes to decrease our CO2 emissions, energy demand, etc. And silicon is one of the metals that we work a lot on, also for solar application, refining of these, etc. I would also like to mention that we have a big center that my group is running here called Zero Emission Metal Production. So we're very much into this, and all these industries that you see in this map are connected to this center. So we work a lot on decreasing emissions here in Norway together with Europe, of course. But now we talk about silicon. And as I guess many of you know, it's a process or metals in general we are producing with carbon as reductant. And when you put in carbon as reductant, you get out CO and CO2 as an off gas. And this is something we would like to avoid. So what we do is that we charge our furnaces with silica and carbon, and then we put in a lot of energy, and then we produce tap metal at the bottom. Here we tap metallurgical grade silicon. And yeah, that's what we are at least working on in this process. And then we capture the off gases. And you see it's about per ton of silicon, we produce about 5 tons of CO2. So this, of course, needs to be decreased. And also the energy, you see the 11 to 13 megawatt hours per ton of silicon. So we need a lot of energy here. And we also produce fines in this process. So in order to be more environmental friendly, we have worked on a process to decrease the energy consumption and also the CO2 emissions, which I will mention soon. But first, as I said, EU's, as you probably know, there are a lot of initiatives from EU that we need to act and be greener. And this is one of the act, the Green Deal Industrial Plan. And in this one, there's an interest in decreased energy consumption, where we focus on many critical raw materials and also to do something on the electricity side. But just looking at all the materials that we are having in one map, and you can see some are more critical than others, and silicon is considered as low, but you can see the streams from the silicon box, the greenish one, it goes into all these things that we need for the in the transition. So we use it both in renewables, here represented as PVs, and also batteries, which are two of the products that we are working on in this project, also e-mobility and defense and space. So silicon is used in a wide range of applications that we need, and that's why it's critical. And when we just look at, as I said, it's critical for Europe, you can see, and it's mainly because we are so dependent on China, about 64%. When I got this map was produced in China, and you see Norway, we have a share of 5%, so we are quite important for Europe when it comes to production of silicon. And where you see where it goes, about 20% goes to PV. It changes, of course, all the time. Silicon has a big share, but you can see the aluminium alloys. Lots of the silicon produced is actually used as an alloy element into aluminium. And this is something I would like you to keep in mind when I continue here, because there are different strategies then to meet these climate goals for the silicon industry to reduce their emissions and energy consumption. We look at different ways of doing this to supporting the industry. One way is to use new reductants, like replacing fossil carbon with charcoal, which is something we look at. You can blend this with a raw material, silica, make composites. So you have different raw material mixes. You can use metals as reducing agents instead, or hydrogen. It's difficult for silicon, but you can use it for other cases. Here, plasma, electrolysis, carbon capture, storage, and utilization. So there are just a few. And what we looked at in this project is metals. We looked at using aluminium as reductant. And why is that? As I mentioned earlier, aluminium is roughly 50% or 40 to 50% of the silicon produced today is used by the aluminium industry as an alloy element. So 40 stated here. So why not use it as a reductant to produce a product at the same time? So that's why we looked at aluminium as reductant. And also the reason is that aluminium industry also has its challenges, because first of all, it's about 20 times larger than the silicon industry. So we produce much more aluminiums. And a lot of the aluminium today is shipped out of Europe. And we need to keep the scrap in Europe, make it valuable. So this is a challenge that Europe has. And the tendency is that this is increasing. So we really need to wake up here. And that's also with other resources that we're losing. And a lot of dross is also produced, which is something that it's a waste product that you skim off. So it contains oxides as well. This is pre-processed in many ways, but with a quite dirty process. So we propose a more environmental friendly way of reusing it. So yeah, and it's of course since it's an alloying element, it's also of interest for the aluminum industry to have CO2-free elements that they alloy into their products. So if we can sell this CO2-free silicon to them, that's of course a plus for their end users. So what we proposed, because this is the Resilex from our side, from Anteno, is linked to the Sisal process, which is another EU product that just finished. So you can see the traditional silicon process to the left. What we do, as I said, is that we replace the carbon with aluminium as reductant, which means that we don't produce any direct CO2 emissions from this process. So what we instead produce, so you see we produce silicon and alumina in the slag. So silicon is a metal, aluminum in the slag, and we put in aluminum dross or scrap as reductant. And that means no direct CO2 emissions. We also have other emissions that we decrease, like NOx, which is a problem of carbon. We need less energy because this is an exothermic process as compared to the previous one, which is endothermic. Also, this is an efficient way of using scrap and dross, since you can avoid other especially for dross, dirty processes, and we don't have any problem. The other process you need to have, you can't have fines because it's a solid vapor reactions, while our process is solid liquid reactions. So we can also allow fines, which can then be utilized in this process. So as said, what we produce, 2 projects, this alloy silicon, Sisal alloy, it's a mix of calcium, aluminum, and silicon, mainly silicon, that you will see later on that we refine in this project. We have the slag, which needs to be utilized because we see that as a product as well, which can either be used to produce high purity alumina. You can use it to put it back to the electrolysis cells and produce aluminum again, or you can use it as an additive in cement or as a refining slag in steel production. So we are looking into a circular process, which you can see here. And in Resilex, here we are. So the other part is Sisal, which was done in another EU project. So what we do is that we produce this silicon via the aluminium reduction, and this alloy was metallurgical grade silicon. Or this is the alloy that we then mix in Resilex with kerf, which is a waste sawing dust from the PV industry, and so we refine our product with the kerf from this other value chain and produce high purity silicon. And in other projects, we have looked at the slag, both for the putting it back to the electrolysis set to produce high purity alumina. We also looked at other ways of utilizing the slag. So this is a bigger picture of what we're doing. But looking at the refining. So after you produced it metallurgical grade silicon, what we also did in this process is to refine it to high purity. And there are different ways. Siemens process is the traditional way, where you mix metallurgical grade silicon and react it with hydrogen chloride, produce trichlorosilane, and then you have to purify it, you have to distillate it, and then also you produce this vapor. So there's a lot of energy in this process. So it's quite energy intensive, but you get out very high purity silicon. There are other ways that we are looking into in this project to reduce also here the emissions and the energy consumption. So some ways that you can do is slag refining, vacuum refining, acid leaching, or you can look into crystallization by directional solidification or this Charpsky method. And we have looked at these 2 and compared the efficiency of these 2 in this project. And so what we've done then is that we first, in the Sisal project, we produced the Sisal alloy. And as you can see, it's a mix. It has about 74% silicon, 10% aluminum, and 16% calcium. Then we did the refining. We mixed the slag, this alloy with some curve and some slag, calcium silica slag, and we produced metallurgical grade silicon that we then did a directional solidification on, or the Szynkowski growth process. So we produced these 2 ingots. And here you can just see the pilot experiments that I mentioned. So we have produced both in 50 kilo scale and 400 kilo scale. And the one we did in 50 kilo, the purest metallurgical grade silicon we got out after this refinery curve was about 98.91%. And from the large scale, we reached 97.79. And here you can see the tapped metal and also the separated metal and slag at the bottom. So this metal then, we did this directional solidification process. So we put it into our ladle, and you can see it's mixed with impurities. And the theory behind this is that you slowly solidify it from the bottom. So the impurities in theory should end up at the top, as you can see there to the right, the reddish part. And that's what we did. Here you can see our furnace. We produced about the 12 kilo ingot, and then we took 10 samples to the middle and to the side to understand how pure our final ingot was. And surprisingly, and was also Mickael saw when we sent it to him, it was not so pure. We reached only 3N. And the purest part was at the bottom and at the top and the side. So it was more dirt in the middle. And the theory was that it should be less pure at the top. So we got something else. So this method didn't work very well for us. And that's why we also tried this other Szynkowski process. And the difference here is that you charge it here as well, impurities, and then you dip the seed and you rotate the crucible. And then first we did some fishing to get rid of the impurities. You can see on top here, it's floating on top. So we tried to fish it up and remove the top part. And then we started to pull our crystal. You can see the pulling process. And here we use material from the large scale trial, and it was, as I said, 97.79% pure, and to ensure that we could tolerate, because it's quite dirty from this perspective as a starting material, so we blended it in with high purity silicon, electronic grade, so 50-50, and the total mass was then 30 kilos. After we blended these 2 streams, we had a starting purity of 99.52%. And here you can see the pulling again, and it's turning, it's lifting out. And the final purity, what we were able to reach from this starting percentage of 99.52 was 5N at the top. So the first 70% of the ingot had a purity of 5N. And then you can see there in the crucible that we have some post-scrap and slag left. We may have written a paper and presented this in this conference. And the main purities that we see are mainly calcium and aluminum, which of course comes back from the scissor process in the beginning. Here we also in this project have done, we have simulated the process in fact station. We're doing LCA on this. And you can see here that this is the second round production based on the fact stage calculations then, and also on the results that we have from the process. So this is a continuous process. And what we do is that the refining slag from the first round and the pot scrap and purified 3N silicon, the bottom of the ingot is recycled back. And so that we kind of, the pot scrap is taken out so that we get to sell that as a product, so that we get a purer and purer process in the end and get rid of some impurities. And these are also valuable products in the market. And in the FCA case, we set the system boundaries, both for LC and LCC in this project around the whole process. So we start with SISA, where we have the dross and quartz and everything. And then our process is the SISA process all the way to the high purity silicon, this 5N. And we compare it with the Siemens processes, that is the commercial process. And a conclusion then that we have approximately produced 200 kilo of metallurgical grade silicon. This was with the curves. So when you add up the large and medium scale experiments, and the purest metal that we obtained was 98.91% silicon. And I said major purities was calcium aluminum. We also had some iron in that ingot, or in that metallic grade silicon. And from that, as I've shown you, we produced two types of ingots. One with directional solidification, where we only reached 3N, and also then this crystal pulling where we're able to reach 5N. And these ingots were all sent to CA. So Mickael will now tell you what he did with our material that we produced. Thank you.
Thank you, Maria. Now you provided really the bridge to Mickael's presentation. In the meantime, I'm telling to our audience that you can post a few questions now. We can try to answer now, or then we will answer at the end. In the meantime, Maria, I wanted to ask you something. At the beginning, you mentioned the let's say the fact that China is dominant in the silicon production, and then you talked about the fact that for the production of this silicon ingot you used slag and kerf. So in a scenario where we upscale this process, where this waste streams come from in order to feed this process in a wider scale?
That's a very good question. I mean, really, Europe, we have lost the whole value chain, to be honest. We don't produce PVs in Europe today, so we need to bring it back so we get some kerf produced in Europe. Also, we can take PV cells. I mean, when we discard them, we can clean them. I mean, remove the backsheet and the silver through leaching processes, which is also something we look at here, and use them and melt them in. So we can also use the cells as is. But we really need the same with the scrap problem. We are shipping out a lot of value from Europe that needs to be kept, because we have a lot of resources here. Even though it's produced in China, when it's bought, we can use it and reproduce it. So we really need to be better in taking care of our resources in Europe and make profitable business cases.
True,
That's
true.
Problem
Actually,
in recycling.
This allows me to mention that during Resilex workshop earlier this year with the Association of Mining Companies in Europe, this topic of the export ban on certain products came to the surface, because Europe is exporting a lot of scrap metals, scrap minerals that can be potentially used in value chains in Europe like this that we saw now. So yes, this is definitely a theme. And so now we can move to Mickael for the second part of this story, which starts from where Maria ended her presentation. So Mickael, the floor is yours.
Thank you for the introduction. Thank you for inviting me for this webinar. And thank you, Maria, for your presentation. It was very interesting. Do you see my screen? It's okay?
Yeah, put it full screen.
Yeah, like this.
Good.
So today I'm going to present the work performed in the frame of the Resilex project. And the presentation is titled as From Silicon Waste to High Purity Solar Cells. First, I just want to start by saying some words regarding CEA. So CEA is a key research player at the service of the French state and economy and citizens. And CEA is organized, I would say, in 4 main domains. The first one is dedicated to the low carbon energy activities. The second one more dedicated on the digital activities. The third one on the future and healthcare, and the last one more secret, dedicated to the defense and security. As you can imagine, I'm working on the low carbon energy directory or routes, and within this big domain, I'm part of the LITEN, so LITEN, the Research Institute for Energy Transition. And within this institute, we aim to develop cutting-edge technology to reach carbon neutrality by 2050. And we need to see to empower industry and catalyze value and job creation, mainly in France and in Europe. So the LITEN is located in 2 main places in France, so in Grenoble, on the Giant campus, and in Chambéry, where I am working every day. So I'm working here at ANS campus. So within the Liten, we are more or less 1,000 employees with a budget of 160 million euro, with in the range of 200 industrial partner working with us. And to perform our research activity, we can use more or less 12 experimental platforms, and we have also patents in the range of 2,000. And within this activity, or within this Liten, there are different strategic research areas. So the photovoltaics, the activity dedicated on the batteries, hydrogen, e-fuels, system grid and energy efficiency, and the last one dedicated on the materials and circular economy. So I am here working on the photovoltaics research area. And if we made a zoom on our solar platform, which is located in Chambéry, you can see on this picture the different way domain of work. We are working at the cell process level. We are focusing on two cell process, so the heterojunction cells and the TOPCon cell process, with in our labs, I would say cell efficiency in the range of, we can reach cell efficiency in the range of 25%. And in this domain or area, we are focusing on industrialization toward gigafactory manufacturing. And we also work on the sustainability domain, how to reduce metals like indium or silver within the elaboration of such cells. There are also an activity dedicated on the tandem silicon perovskite cells. Here we reach a record in cell performance record close to 30% on 9 square centimeter cells, and we focus to increase this efficiency on a larger format. And with this tandem cells, there is a problem of stability and the process. So we have a lot of activity on, improve the stability and the processes, and in the same way, increase the cell performances. And there is also activity dedicated to the module manufacturing and eco-design. So here we are working on the shingling, the paving, the interconnection between the cells and the modules. And we also have work on eco-designs by the use of new materials. And on the last part of this slide, you can see a picture of our pilot line, which is able to process cells in the range of 2,400 cells per hour in the best case. So now, what will be the place for PV in the world by 2050? So here are a figure coming from the net zero CO2 roadmap from IEA, and you can see here that there is a push to a massive electrification of energy sources from 20% to close to 50% of the final energy use by 2050 here. And if we look more in detail, what will be dedicated to the solar PV installed capacity. So you can see that depending the scenario used, we plan to install in the range of 14.4 terawatt to 63.4 terawatt, depending on the scenario used for this prediction. So there is clear place for PV installation in Europe. And now, if we I just want to make a focus on what is the situation, or what was the situation in 2023. Sorry, I do not have the last data, but in 2023, what we can see. So on the left, you can see the evolution of the cumulative PV installation. So you can see that in 2023, we reach 1.6 terawatt of installed capacity, and mainly the installation are in China. And on the right-hand side of this slide, you can see the annual capacity growth. And you can see that during the last year, there is an important dynamic during the year 2023 with an additional growth of close to 210 gigawatt of capacity installed. And within this picture, you can see that the European Union represents more or less between 12 to 15% of these markets. And in terms of projection, the targeted production capacity here again, depending the scenario used, can go between 600 gigawatt per year to more than 2,300 gigawatt per year. So there is clearly here again a place for installation. What about the PV solar cells technology? So on the left-hand side, I use a picture information coming from the IRTPV roadmap. You can see that the silicon-based technology dominates the market today. The PERC manufacturer are going to switch from PERC to TOPCon solar cells technology in the coming years, but it's already done, I think. And there is a market share for the heterojunction solar cells should be increased from close to 5% today to something more close to 20%. And you can see here the presence of tandem, which seems to appear in the next step or in the coming years. On the right-hand side of this slide, here I present, I would say, the solar cells technology we're working on at CEA. And you can see that the TOPCon and heterojunction cells today are at ITRL level. So it means that it's compatible with industrialization. So there are factories manufacturing such kind of solar cells with efficiency higher than 26%. It's not the case for the tandem, which is more a low TRL, so meaning that we need to improve and to work at within this research institute to increase the stability, the durability. But anyway, we also have some records worldwide which are higher than 35%. So it means that there is high potential by using this technology. Now we can make a slide dedicated to the specification. What are the silicon specifications used today in the PV industry? So today, I would say that close to 100% of the cells and the module you can buy are made from wafer using a solar grade silicon. So this is very high pure silicon. With a purity level close to 9 to 12 N. So they are manufactured from the Siemens process that Maria already presented in the slide before. And you can find this silicon, this polysilicon, in different forms: chunks, rods, granules, chips. Here, just for your information, you can see on the right a small table which can make links between the 6N, the percentage of purity, and the impurity corresponding. Just for information, if I use 9N purity polysilicon, it means that there is 1 impurities above 1 billion of atom of silicon. So it's a very ultra pure silicon. Here, I just copy-paste screen website from just to give information regarding the current polysilicon spot price. So you can see that in China, if we want to buy this silicon, we need the price is in the range of $7 per kilograms. So it's very, very cheap. In Europe, if we want to buy equivalent, it's more close to $18 per kilograms. Here again, and on the table here, you can see what the solar, the heterojunction solar cell process, what are the specifications for the manufacturer of cell process regarding the wafers they are using. So to manufacture heterojunction cells, we need a wafer with a resistivity in the range of 0.4 to 1.6 ohm/centimeter. We also need N-type wafer, meaning that the dopant is phosphorus. It's changing today. Here again, there is a strong requirement regarding the carrier lifetime over resistivity, and this ratio should be higher than 3 milliseconds per ohm/centimeter. And here again, there are also specifications regarding the oxygen within these materials. It should be lower than 11 ppm-A. So, and for the carbon, it should be lower than 1 ppm-A. So in this wafer, the oxygen is coming from the crucible used for the pooling process. And I just also give you information regarding also another methodology. So the upgraded metallurgical grade silicon, which here reach purity level a little bit lower compared to the Siemens, but we consider this is a minimum quality requirement for solar cell manufacturing if we can reach purity level close to 7N. But you have to have in mind that the main parts, the close to 100%, are coming from these processes. So in the frame of the Resilex project, what we did, we evaluate at the ingot level the photovoltaic properties of the recycled silicon produced by NTNU in order to assess the suitability of this recycled silicon for solar cell production, and in order to define the best way to produce ingots. So it's just in one slide, a small summary of what Maria said. So they produce two kinds of recycled silicon with different using two equipment. So with a medium scale slag, they reach purity level of 98.99%, and with a large scale slag, they reach 97.79%. And after vacuum refining, after additional step purification, so additional directional solidification for the first one and the additional CZ growth process for the second one, they reach, in the first case, silicon purity close to 5N. I think she wrote 3N, so it's in between 2 to 5N in terms of purity. You have to have in mind that within this recycled silicon, there are still some presence of dopant like boron, phosphorus, of aluminium in quite big quantity. But here I just put the number here. And for the other one, after the additional CZ growth process, they reach a purity of 5N with, here again, still a presence of dopant like boron, phosphorus, and aluminium. And in between the two additional growth, you can see that the boron concentration has been divided by a factor close to 5-6. So what we did, firstly, we use the recycled silicon after directional solidification production, and we first pull a CZ ingot with boron and phosphorus concentration added in the feedstock, as if we had used more or less close to 2% of the recycled silicon from directional solidification. So we did this. You can see here the CZ ingot that has been pulled. So it's a small one, and it's a 30 kilogram CZ ingot, but it was perfectly adapted. You can see this ingot has been squared into a brick compatible to the M2 size wafers. The brick has been grinded, and after grinding step, we cut the brick into wafers. So from this ingot, we were able to produce more or less 700 mono-CZ wafer. And this wafer has been used in the frame of the Resilex project for an assessment of the wafer for the first CZ ingot with specific phosphorus and boron concentration. We did two kinds of assessment. First, some measurement of the wafer electrical quality has been performed on 5 different positions along the ingot, and we also measure the behavior of this material under light and under illumination. So this is what I'm going to present in the next slide. So here are the ingots. The wafer we use for this experiment are from the top to the bottom of the body of the ingot, where the wafer has been manufactured. So position 1 to position 5. Here, this is a typical heterojunction cell process we used. And here, this is a picture of the symmetrical layers of these cells. And what we did after step 2, so after the deposition of amorphous silicon layers, we were able to monitor the Curie lifetime at 1/10 to the 15 cubic centimeter injection level, and we also were able to measure the implied VOC. And you can see here on the graph on the right hand side of this slide that so this is the reference wafer cells we'll use. You can see that there is a small decrease of the lifetime over resistivity ratio, which is close to between 1.8 milliseconds per ohm centimeter to something close to 1.4 ohm centimeter, milliseconds per ohm centimeter, which is not so big, but not so bad. Anyway, which is also interesting is you can see here the evolution of the voltage along the ingot. You can see that there is a decrease from 735 millivolts to something close to 7 millivolts. Here you can see that you can imagine that this reduction can be linked to the evolution of the impurity concentration from the top to the bottom of the CZ ingot, and we can imagine that here this reduction is clearly linked to this. We also perform another set of experiments. This is a lifetime evolution under light exposure. So we take some wafer with the amorphous layer passivation, and we put these wafers under 0.5 sun of illumination and at 60 degrees C. Why we did this? It's because these conditions are typically the condition used of PV modules when it's working. And you can see here, it's very interesting to see that the lifetime of this wafer, strongly reduce with the time under illumination and temperature. So this evolution can be explained by the presence of residual boron concentration in the wafer. And when there are some boron in the wafer and oxygen coming from the crucible, we can generate boron oxygen complexes that can, under illumination and under temperature, can reduce the quality of the wafer. This is a light-induced degradation. Yes. Then we perform two other experiments by using the recycled silicon after the additional Czochralski pooling step. So this is the recycled silicon we used, and here we pull two CZ ingots using respectively 11% and 12% of recycled silicon feedstock. And here, this is on the graph, you can see the expected resistivity profile by using this configuration. So we expect having final CZ ingots in the range of 2 to 0.5 ohm centimeter and 100% N-type. So you can see the picture of the experiment. You can see here at the bottom of the crucible, the recycled silicon coming from here, and then the loaded crucible with 30 kilogram of silicon. And here I choose a picture of the body step. So during the pulling step, you can see the seed use, the neck, the top part of the ingot, and here this is the interface between the ingot and the silicon melt, and all these parts are heat shield. Here you can see the final step, so the tail. This is the last part of the ingot that has been pulled before the experiment finished. On that ingot, we measure at the ingot level the resistivity, so we can confirm that we are in a good resistivity range, in the range of 1.62 at the top to 0.5 ohm centimeter at the bottom of the body part used. So this ingot, as for the first one, has been squared, grinded, and cut into wafers. And today, within the Resilex project, the wafers coming from this ingot are used for heterojunction cell manufacturing and experiments. In terms of summary and next steps, so NTNU sent to CEA 2 recycled silicon ingots. In our task, CEA performed impurities analysis on these two recycled silicon feedstock in order to assess the suitability of the waste material for the production of solar cells. CEA pulled one 30 kilogram CZ ingot using the result of the impurity of the GDMS of silicon feedstock from the directional solidification process. CEA pulled two other CZ ingots using the other one. And in the last case, we use 12% of recycled silicon feedstock. And all this ingot met the resistivity and the type objectives, which are compatible for the elaboration of heterojunction solar cells on our CEA pilot line. Thank you for your attention, and I'm pleased to answer to your questions.
Thank you, Mickael, for the presentation. So in the meantime that some people from the audience think about a possible question, I wanted to ask you, maybe it's early, but I know that CI is going to make further tests. Do you see, based on this experience, do you think that it's feasible to increase the percentage of recycled silicon?
I think I can increase a little bit the percentage of silicon. I would say we will see during the next evaluation how the residual boron concentration in the ingot has an impact on the evolution of the cell efficiency, and if it's problematic for the lifetime of the cell of the final cells. If we have solutions to mitigate the presence of boron, I would say we can maybe increase to 15%. It's not a problem. Otherwise, we will need to find additional thermal treatment or processes in order to mitigate the presence of boron inside.
Okay.
Yeah.
Can you disclose something about the tests that you are going to make with the cells produced out of this ingot? I mean, how long these tests are going to be carried out? And
I would say that the first test will be, I think we are going to reproduce exactly this. We are going to take wafer on 5 positions from the top to the bottom. It's really important to do this because due to the segregation, in fact, the quality of the wafer at the top are different from the one at the bottom. So it's important to have this evolution across the ingot 8. We are going to process heterojunct solar cells. We are going to measure the lifetime over the position. We also plan to, as for this ingot, to perform some tests under illumination and temperature, but it will take more than a few minutes. I think it will take 1 or 2 weeks of illumination and of temperature. We are going also to work on the regeneration because if the boron is clearly involved in the reduction of the quality, we can have some regeneration task or experiment in order to regenerate the quality by eating the wafers. And I think we also plan to work on thermal treatment in order to mitigate the effect of the boron. So I think this will be presented in the next coming General Assembly meeting.
Okay. So for news about this test, so please check out the Resilex website and the social media channels, because we will regularly update since it's going to end in the next year. So there will be plenty of results to be disseminated in the coming months. So I don't see any other questions. So thank you very much, Mickael. Thank you very much, Maria. As I mentioned before, this webinar will be available soon on the Resilex website, as well as the presentations. And of course, check out the website and the LinkedIn page to know about the results of these tests that we heard here. Thank you again, and see you next time.
Thank you.
Thank you. Bye.
Bye.